Okay, are we on? Okay, sorry for the le- last minute. I don't know if you ever have that. I think anyone who lectures, you can think about something for weeks, but then you wake up in the morning and think, oh, I got to add this stuff. So I realized from some of the questions yesterday that I hadn't really explained why we look at balance dynamics. That was kind of a significant omission. So um, Hank has been showing figures of heroes. My hero is Charney, I have to say, just an amazing scientist. And there's a quote from Charney that goes back to, actually I don't have it, but it was a letter to Norman Phillips in, I think, 1947. Charney says, we might say the atmosphere is a musical instrument in which can play many tunes. The high notes are sound waves, low notes are long inertial waves in nature. As the musician is more of the Beethoven than of the Chopin type. She much prefers the low notes and only occasionally plays arpeggios in the treble, and then only with the light hand, and then and so on. So I think this was just to say that at least in the atmosphere, ocean of course has huge internal oscillations, but at least in the atmosphere, it's a rather negligible part of the motion when you look at it at first glance. And for example, I mentioned the time series. This is data from NOAA during a surface prep. This is during a 2-day period, May 15th to May 17th, at a single station. A cold front is coming through with a squall line. This is a very intense weather system. But that curve, and you see it's very high resolution. It's incredibly smooth, incredibly smooth. You would think you would generate all kinds of waves. I sort of sketched this out orally, but I didn't really lay it out. This was from a thesis of a student of mine, Ian Chan, who sadly, he's very talented, who now works in the financial sector. But so we have the full system. Well, of course, there's moisture and various other things, but in terms of dry dynamics, the full system is a compressible system. UVW, 3 components, the density, temperature, plus the ideal gas law, or just in general, an equation of state. But if you impose incompressibility condition or hydrostatic balance, you can filter the sound waves, and you get to incompressible models or primitive equation kind of models. You can also filter inertial gravity waves with the geostrophic balance. So this is 5 equations, 2 constraints brings you down to 3 equations, 2 more constraints brings you down to one equation. You have this QG equation. So of course it leads to reduced models, which of course one thing are easier to solve, and especially for QG. In fact, Charney really was the one that came up with the theory of QG, and he did tremendous. I mean, all this theory, Charney Elias and Charlie Drazen, Charney Stern. I mean, there's just so much. Most of the theory, if you look at the books and of large-scale dynamics, ultimately come from the QG model. So that's a very important use of balanced dynamics. The other thing is that someone mentioned, I think Freddie mentioned geostrophic adjustments. This was just an illustration that Ian had in the introduction for his thesis. Actually, a good place to look for reviews is always introductions to good students' thesis, because it goes through the whole thing. So this is initial state at t equals 0, and we have u is 0, v is 0. I guess they're both on top of each other, and then we have just an edge in the height field. And as you know, what happens is this projects in the linear system onto both the vortical modes and the inertial gravity the gravity waves, and the gravity waves propagate away. So you see at T15, T30, the gravity waves are propagating away. In this system, you don't damp the gravity waves; you just let them propagate away to infinity, and you're left at the end with this balanced state, with a wind field, a zonal wind field, a V in this case actually, which is in balance with the height gradient. So this is all the kind of physics of it, and so we want to understand balanced models theoretically for reduced models, but also it's important. So what happens here, of course, if you make an initial condition, this was one of the other motivations, apart from the theory, was the practical issue of weather prediction. Actually, Charney was also involved in the first numerical weather prediction, and they initially, the first numerical weather prediction was Richardson, but the first computational weather prediction was Charney, Fjordhoft, and von Neumann. They used a balanced model for that first forecast, but very quickly they realized it wasn't accurate enough, and they wanted to go to the primitive equations. But there was this problem. Because the observations of errors, and even though the actual amplitude of the gravity waves may be small in the real system, because of observational errors, those will just project randomly. And so this is an illustration. Sorry, I did this too quickly. Temperton and Williamson. This is a model, and this is surface pressure. And they just take, if you just take this data, which is, we say uninitialized. Of course, it's initialized in a mathematical sense because it's the initial condition. But what we mean by initialized here is a balancing of the initial state. So if it's unbalanced, what you get is surface pressure oscillations that go way up and down because you're projecting onto these gravity waves, and you're basically exciting this geostrophic adjustment process. And just as we saw from the observed surface pressure trace, the atmosphere doesn't do this. So you can do a linear balancing, which is a geostrophic balancing, and that helps a little bit. But you still have oscillations. But if you go to a nonlinear kind of thing, what I was talking about, Charney balance, that was another Charney 55. If you go to higher orders of approximation, you can get a smaller initial amplitude. And here you see that I wouldn't say it's zero, but it's basically now down in a very small amplitude. So this was actually used practically in a weather prediction from about the mid-50s through the 80s, and there was a very sophisticated method called nonlinear normal mode initialization that really used this slaving approach in effect up to a few orders. But then, as I say, it got superseded. Actually, I think the problem was once the people went to variational methods and they couldn't compute the adjoints, and then they gave up and applied time filters and various things. Okay, now the other thing that happened. So I'm not thinking about these things much these days, which may show I'm a little bit rusty. Main thing I'm thinking about, because I moved to Reading and I decided, okay, I'm going to maybe a number of people late in their career have these things. I'm going to do something really hard. I'm going to think about climate change because it's not really a very well-posed problem. And it turns out that psychology is a big part of this, I think, how you approach it. So I thought I would like to give a talk on psychology and climate change. It really should be an evening lecture, but philosophically, but over wine probably too. But the lecture schedule is so packed. So actually, I had originally planned 5 lectures, and then when it went to 6, I split one into 2. So what I think I'm going to do, since it's a late afternoon anyway, and I don't think it's not a good time to give you anything too heavy. I mean, this is heavy, but in a different way. So what I'm going to do in the afternoon, so this morning is going to talk about turbulence, like I talked about initially, but then I'm going to have a primer on Hamiltonian dynamics just for about half an hour, because I suspect not everyone knows even about Hamilton's equations and so on, and the concept of symplectic dynamics and Noether's theorem. So some pretty basic but not well understood aspects of Hamiltonian dynamics, and then I'll pick up on the Hamiltonian geophysical fluid dynamics that comes in the pseudo momentum, where it ties in basically as the basis for the theory of waving flow interaction. And then I'll switch. Maybe we take a quick break or something, and then I'll switch to kind of a seminar. Of course, I'd like to have a discussion on this too. So I would somehow prefer if this wasn't taped, but anyway, I guess I can live with it. So that's the plan for the afternoon. So and this morning. Were there any questions on the balance stuff before I get going? Okay. Right, 2D and shallow water turbulence. So we've seen the vorticity equation several times now, the 2D order flow. You should know that has 2, if it's an inviscid system, it's got 2 invariants, and that's pretty easy to see because, so if we take del squared psi by dt is minus Jacobian of psi del squared psi. So if I multiply this by del squared psi on both sides, use Hank's trick here, and integrate over the domain, then of course here I get d by dt of a half del squared psi squared, and then here I get the integral of well, it's Jacobian. I can absorb it inside, and I get a half grad psi squared. And as long as I have nice boundary conditions, that'll be 0. So this is the entropy. Oh yes, sorry. And then if I do the same thing with multiplying by psi, so this is a little more tricky, but I integrate by parts first. So I got del psi grad psi t, and then minus grad plus, I guess here, grad psi. No, sorry, grad psi t. Minus, right. And then how am I doing? This is a funny notation with this bracket around the whole thing. So then I get yeah, d a half psi squared Jacobian of psi dx dy. So again, I can absorb the psi in the Jacobian, and that goes to 0. This will be 0 because either it's doubly periodic, or if you have some sort of a channel geometry, psi is constant on the boundaries, and this integrates around in is circulation. And by Kelvin's circulation theorem, that must be 0. So these go to 0, and this thing just becomes a half grad psi squared, and that's the energy. So in the barotropic system, without the free surface, this is the there's also the QG version with the free surface. Then the energy is just a kinetic energy. So these are the two conservation laws: the energy and the entropy. Now, if you take a spectral Fourier series, you can see that you just count the number of derivatives. This has two derivatives. This has 4, and so the entropy, if you have a wave number, usually in this context you're assuming it's isotropic, at least in the classic problem. So we just have a scalar wave number. Then the entropy, which is Z here, entropy is wave number squared times the energy. So if you know anything about three-dimensional turbulence, a characteristic you have this, you only conserve energy, you don't conserve entropy. There is helicity, but it's a topological invariant, and it doesn't constrain. It's got some constraints, but it doesn't constrain the energy in a strong way. And so what you get is a downscale cascade of energy down to small scales. But you can already realize that if you take a certain amount of energy and you move it to high wave numbers, then k squared's increasing, so then Z's going to blow up. But if you're conserving Z, that isn't possible. So it's clear that you can't have a downscale cascade of energy because of conservation of entropy. And I think this was actually realized by Taylor in 1917 originally, and has been studied ever since. But it leads to the peculiar properties of two-dimensional turbulence, which is called the inverse cascade, which I'll talk about in a second. And this is the basis for the large-scale flow structures of geophysical fluids and the formation of coherent vortices. And actually, it's a classic problem in mathematics and physics. So 3D turbulence is, of course, an even harder problem, but even 2D turbulence isn't really solved. I mean, the mathematicians would say they solved it because they have existence and uniqueness, but actually, in terms of the properties, there's still a lot of you get a lot of papers in the physics literature on this system. Now, so I won't actually talk much about vortices, but in fact, I kind of I had several misfortunes as a PhD student. First, I actually started with Charney, but then he had died, and I wound up with Peter Rines. But then Bill Young was a student with Peter Rines, and they had just published Rines and Young, so then I was in the shadow of that. And then I thought, well, okay, I'm in the atmospheric program. Bill is in the joint program. At least maybe I can shine in the meteorology department. But my co-student was Steve Zibiak, who discovered Kane-Zibiak. And then for my thesis, I thought, okay, people have looked at 2D turbulence, but the atmosphere has these jets, and so surely we should look at the turbulence in the presence of jets, right? Seems like an obvious thing to do. And then McWilliams published his paper on coherent vortices, and the whole field went to coherent vortices. In fact, I was even one of the referees of one of my thesis papers, where I just had a jet with beta. And I didn't get coherent vortices because with those values of beta and that kind of jet, you just don't get vortices. And the reviewer said this was of no interest because I didn't get vortices. But I'd chosen the beta and U based on the atmosphere. I mean, it was physics. But anyway, in the classic case, what you get is this. If you start with just noise, this is X versus Y here, and this is vorticity, and you just start with this patchiness, it emerges into vortices. And Bartello and Warren have a very nice similarity theory of this. So that's the kind of classic 2D problem. But actually, as I'm going to talk about, I'm not going to focus too much on vortices. So there's a number of different arguments for the inverse cascade. This is one of the classic ones, and I've just used the cartoon from Jeff Alice's book here. If you say, like, okay, we have an energy, and let's assume it starts in a localized set of wave numbers, then just by nonlinear processes, we can expect that this will diffuse somehow, right? I mean, that's a general principle. And so if you look at for K naught is the original, is the starting wave number. And if I look for the spread around that, so K minus K naught squared times EK. So if I write an equation for that, I get three terms. I get d by dt of K squared E, I get d by dt of minus 2 K naught E, and then I got d by dt of K naught squared E. And if I just assume sort of a arrow of time, so you can't prove this, but it would be an ansatz that would be some sort of maximum entropy argument, I guess, that this will spread. So we argue that this thing should be positive, at least at initial times. But this is just the entropy, so that's conserved. This is just the constant times the energy, so that's conserved. So the only term that can change is this one here, and you infer from that the first moment of the energy spectrum must move up to smaller wave numbers, which is a larger scale. So it's pictured here that if you spread, then you must also march upscale. If you go through the same argument with another power of K in front, then you can also argue that the entropy must move to larger scale. So that's one of the arguments. It's based on the initial value problem. So the classic picture of turbulence, in a way, this goes back to Creighton. So the idea is we have some stirring. So of course it's an idealized setup. You say we have some kind of a stirring, and maybe I should define what all these things are, because I didn't do it here. So epsilon is the energy injection rate, and eta is the entropy injection rate. And then, of course, it's going to be the case. I don't have a wave number here, but eta is going to be K. Let's call it K forcing squared times epsilon. So there's a constraint by the spectral relationship between energy and entropy that these things will be linked. So you imagine that you're forcing at some narrow range of scales. And then then you argue, okay, you can't have a downscale energy cascade, that's prohibited, but you can have a downscale entropy cascade. And similarly, if you turn it the other way around, you can't have an upscale entropy cascade, because that would be prohibited by conservation of energy, but you can have an upscale energy cascade. And so you hypothesize that there are these ranges, and if you, I won't go through the argument, but one of the classic arguments is to assume that the dissipation occurs only here, and the forcing occurs only here, and then you basically asymptotically, as these scales separate. Of course, for finite separations, there's always going to be, you can't have zero entropy transfer. It can't work, but it works in the limit of the separation. Of course, you might argue, where does this dissipation? Well, this dissipation is obvious. This one's a little more problematical, and if you're really wanting to get clean experiments, Brad used a linear drag. People use a hypoviscosity, del to a minus power. So you can play tricks, but this is the classic picture. Now, if you usually in books, this is these power laws are coming from a dimensional analysis, and actually this is the same power law is in 3D turbulence, because it's the same dimensions, but the interpretation is different, because in 3D turbulence you're arguing that it's a downscale cascade, in 2D turbulence you're arguing it's an upscale cascade. Now, and Charney also so the idea in the atmosphere is that if you're using a barotropic model, of course there's no barotropic instability to speak of, but the forcing is coming from baroclinic instability. So sure, the forcing of climate is coming from the sun, but then that gets converted into a baroclinic energy, and because of the baroclinic instability, that has a preferred scale, set of scales somewhere around here. You'll note there isn't an actual wave number here, but the idea is that baroclinic instability will generate this noise in the system at a preferred scale. There must be radius, and then it can cascade away from there. Yep. Well, of course, what you're assuming is that this epsilon is the injection rate, and eta. So of course, in a quasi-steady state, this is a quasi-steady argument, then the dissipation rate has to balance, right? So the dissipation equals the injection. So what you're assuming is that there's something that depends on the energy injection rate or the energy dissipation rate, but there's nothing about the sign of the transfer built into these arguments, into these dimensional arguments. So you have to use another argument to infer. You can't get that from the dimensional analysis. You have to use some other argument. So we were supposed to give you exercises. I'm glad I didn't spend too much time preparing them because you don't have much time, but I thought I would give you one. So because I had an argument with a student who was, I guess we were looking at this is alpha turbulence, which I'll talk about in a second, and then it's not necessarily obvious what the dimensions are. Of course, it can't be dimensional analysis because a computer doesn't know what the dimensions are. So there's a more general concept called a scaling symmetry, and so that's and I just wrote it out. Sorry, it was faster to do by hand. So we'll post this on the web. So as an exercise, why don't you derive these power laws from scaling symmetry? And there's you won't look at it, but this is a very general theory, and there's a very nice book by Olver in 1986 called something like Lie group symmetries and PDEs. Do people know that? So the idea is, we have I'll just quickly run over, and then I'll leave this. So this is our equation, and we just consider a transformation where you pick a beta here, and we just imagine that time goes to beta to the r times t, x goes to beta to the s times x, and the psi goes to beta to the p times psi. Now, if you require that the whole equation be similar, in other words, it's invariant under these transformations, then you get a constraint. You should show that you get a constraint between S and R. That's the first thing that you have to derive. And then the second is look at these power laws. So the first thing is you assume an energy cascading inertial range. So the assumption there, so this is obviously an assumption, is that the energy this is the spectral density. Okay, so actually very important. To get energy, you have to integrate over k. So dk is a unit of energy, but E of k is a spectral density, and you assume that can depend. There's a constant, of course, but that can depend only on the energy injection rate, because it doesn't know anything else. All it knows is the energy injection rate or the dissipation rate equivalently, and the wave number. So actually, there's no sign here. The energy transfer could be going up or down scale. And then just from there, you should be able to show that these R and S are independent, of course. You can vary them. And if you just argue that show that this energy range has a similarity, you get n equals 2/3, and then k to the minus 5/3, the classic one. And then the same thing if you do for the entropy. You should be able to derive this, and you get the k to the minus 3 power law. So it's a more general concept. Scaling symmetry is a generalization of dimensional analysis. And if you have some time and want some fun, you can do this for this model of alpha turbulence. So which I won't really talk about. Isaac might, I suppose. So there's a generalization where you just write the equations this way, and rather than vorticity, we have, and usually it's so minus del squared, but alpha over 2. So when alpha equals 2, it's this system, but alpha can be anything. And then the energy, just because of the sign, I've got a minus sign in here, so the energy is a half times psi times theta. And then these are the answers, and see if you can derive those. Okay, so I will, yeah. And actually, just as an aside, I had a former student, Helen Burgess, who's now at St. Andrews. The nice thing about these equations, I mean, you can pick alpha to be it doesn't have to be an integer, right? I mean, why not? So So people have looked at alpha 1 is the surface QG model. There's an alpha is -2 is this Charney Hasegawa Mima model. So there's a few other cases. But Helen looked at alpha. So as I say, you can derive these spectra, these power laws, which are functions of alpha. So when alpha is 2, so this is a model where, but very clean. So you force it at the very small scales, and actually the problem is you'll get coherent vortices, right? So we don't want coherent vortices because we want to use these Kolmogorov type arguments. So the way that you suppress coherent vortices is if you force in the dissipation range. So it's a bit of a contrived system, but it's a system which has a hope of behaving this way. And then you get an upscale cascade, and we don't want to monkey with this large-scale dissipation because there's issues about how that might affect the answer. So she just stopped before the simulation got boxed in. In other words, until the energy before the energy reached the largest scale. And you see that for alpha equals 2, that's a pretty beautiful agreement when you say this is a complete decade. Alpha 2.2, it works. Alpha 2.4, it works. Alpha 2.5, it doesn't work anymore. Alpha 2.8, alpha 3. So by the way, this is numerically observed. So there's kind of it's a very interesting thing, which I won't go into, but it's and actually she used a closure model like what Brad talked about, something called EDQNM to try to understand this. Okay, so back to 2D turbulence and actually observations. So I'd actually Charney comes in again. So I was a summer student as an undergrad, and I was I think at the time, after third year, I was pretty much set I wanted to do statistical physics. It seemed like the really interesting area. But I got a summer job in a climate laboratory with a guy called George Bohr, and they were building a climate model for Canada, and this was in the late 70s. But George was interested in diagnostics, and so they had just developed the first global atmospheric data set ever. There had been piecemeal sets up to that point. FIGGI is the meteorologists are fond of these double acronyms. FIGGI is the first Garp global experiment, and Garp is the Global Atmospheric Research Program, and Charney was one of the big drivers behind Garp. So they produced the first data set that was truly global. It was for 1 month, January, and for January and July in a single year. So there wasn't much to it. But actually, for this purpose, it was perfectly fine. So George asked me to analyze this data and look for 2D turbulence. But the first thing he had me do was to read Lorenzo's monograph, The Nature and Theory of the Large-Scale Circulation of the Atmosphere. That is amazing, amazing book. Probably you don't want to read the final chapters on negative viscosity and so on, but the first part, it's just absolutely beautiful. And the second thing he had me do was read Creighton's papers, which seems a bit crazy, but for someone who was keen on statistical physics, boy, that was a hook. So I really got motivated by this. So if you plot the kinetic energy versus, of course, it's you're on the sphere, so the total wave number is the spherical harmonic index. And if you plot the kinetic energy, of course, it's very complicated at large scales. And also, if you decompose, stationary is the time average, so the monthly average. And the largest scales are dominated by the monthly average, and especially by the zonal flow. But the transient, which is deviations from the monthly average, and this will be, I don't know what the frequency was. It was probably just 1 day or something. It might have been 12 hours. And then what you see is this thing. And it's pretty damn close to -3. Of course, you can question this and all sorts, but it was kind of amazing. People had seen hints of this also in zonal spectra. And then if you plot the spectrum as a function of the wave number, so this is in spherical harmonics, so n is the total spherical harmonic index, m is the zonal wave number, so n minus m is the index for the Legendre polynomials. So isotropic would mean that the lines should be flat at constant n. And above about wave number 8 or so, you can see, okay, there's a fall off here, and actually this is connected with the tropics because these are global modes, but really it's incredibly close to being fairly isotropic. So that looks promising from a 2D turbulence point of view. then you can look at the fluxes. So you can derive from actually these terms here. You can just where do I have it written? Oh, well, I did it this way. But if you can, if you had the psi out front, let's say, then of course this will integrate over the whole domain. But you can also, if you express it in terms of wave numbers, then it'll be pluses and minuses of different wave numbers. This one. Okay, so you decompose things spectrally. So in a planar geometry, you have a Fourier series, right? And you have the IKX or the ILY. On the sphere, the spherical harmonics are the eigenfunctions of the Laplacian. So as Brad, I think, mentioned, in the zonal direction it's just sinusoidal, but in the meridional direction it's these Legendre polynomials. So it's just that you plot it this way just because you constant n. So in the planar case, you would have a kx and a ky, and then isotropy would be something like this. You could plot it differently, but it's been a convention just so that and I'm not sure what the origins of all this, but it's just that the energy is a function of so n is the total, but rather than being a sum of the rather than being a square root of the sum of the squares, you can think of n is equal to n minus m plus m, and this is the zonal wave number, and this is the meridional, the Legendre polynomial. Okay, so you can think of this as being a meridional wave number. So except it's more complicated, of course, because Legendre sorry, n minus m is the meridional wave number. So this is the total. So if the energy is isotropic, it means that it's a function only of the total wave number, which would be analogous to that. Does that make sense? Okay, so two issues. So spectra is fine. That's pretty simple because it's just a function of the wave number. When you compute the fluxes, so what you have are these triple correlation terms, and as Brad was saying, those can be represented in wave number triads. So you can interpret them as exchanges of energy and entropy within triads of interacting triads. If you integrate over all the triads, it has to be zero because you're conserving energy and entropy. But for any particular wave number, it could either be a source or a sink of energy. And so when you plot the energy flux, this was up to, I should have said the first data set here was only up to T32, triangular truncation 32. This is 40. It was a slightly higher resolution version, which I then analyzed in my thesis. So, but if you take the total energy flux, you see it's negative here. So this is a spectral flux. So it's defined such that it's you start at zero. Well, you can start here. You can start either way because there's zero at both sides, and you just integrate. And a negative flux means that the energy is going to the larger scales, and a positive flux means it's going to the smaller scales. So what you see is that there's a negative flux which is dominant here, and then it goes up and over there. So where this flux is increasing with wave number, you imply that there must be a source. So the idea is that a baroclinic instability must be pumping energy in somewhere between wave numbers 10 and 25 or so in terms of the spherical harmonics. And there's a small downscale flux, but there's a very large upscale flux. And if you do the same for entropy, you get actually almost no upscale flux, but you get this very big downscale flux. So you could say, okay, this confirms 2D turbulence. We have a upscale flux of energy and a downscale flux of entropy. There's two problems. One is that if you decompose into the stationary and transient part, so there's actually three terms because if you have a triple correlation, terms like this or so on. So if you have a function of psi, if you have a triple correlation and you take a time average, you're going to get this term, and then there's going to be this term, and then there's going to be three terms, which are the cross terms. So it's going to be the way I've written it. I'll just say psi. Um, so let's say psi prime, psi prime, psi bar plus cyclic. So that's just all three terms. There'll also be a term, this one, but this will be 0, as Brad pointed out. If you just average over a linear term that's got a 0 mean, then it'll be 0. So this one goes away. So you wind up with three terms. So there's the mean one, but actually because the stationary flow is mainly zonal, you know that the self interaction is very small. So indeed, this little bump here is the stationary self interaction term. This term here, the dashed, is the classic, what you would assume 2D turbulence should be in the transients. That gives you this dashed curve here and the dashed curve here. But then there's this mixed term here, which is actually a wave mean flow interaction term, and that's how the two different bits of the lectures will come together on Friday. So I won't talk about this much here actually yet. So this actually is pointing to the fact that actually a lot of the upscale energy cascade is not really coming from the transients. So do you really want to call that an upscale energy cascade? It's something else. It's dominant. Mind you, for the downscale flux, it's actually not a small term either. The other issue, though, is that when you do this, you're only integrating over the wave numbers that you have, and you know that there's triads that you're missing. So unlike a spectrum, the spectrum at wave number 30 depends only on the scales at wave number 30. But the energy and entropy nonlinear terms at wave number 30 depend on wave number 50, let's say, and we don't have them. So we know that this isn't correct. This is a truncated version of what we have. Yeah. Oh, time scale. So this is just a monthly average. Well, you don't want to. Yeah. It wouldn't change to first order, I would say, in terms of these broad things, because you're getting the stationary is mainly going to be the seasonal cycle. If we're contrasting, let's say July, so you can look at different years. So in detail, certainly will. And actually, people have looked at. This was a long time ago, but people did look at blocking in the 80s. With these, actually, so you can pick up blocks, for example, if you look at a 2-week period with blocking, just that you don't really want to use spherical harmonics because that's a global thing. So if you want to look at something local, so you might do wavelets or something, but people have tried to look at a big blocking episode using these things, and you can see a change in the upscale flux. So it will be reflected. But fundamentally, I'm going to argue that this is something which is just a basic part of the fact we have zonal mean flow in the system. Yep. Right, but they're not, is the problem. So that's So that's part of the issue, and I guess I'll talk about that a bit. Possibly Friday, yeah. So I mean, well, the other thing is it's just not an isotropic system. So usually you say homogeneous isotropic. The atmosphere is not homogeneous, nor is isotropic. So yeah. But anyway, so it means that maybe you should think a little bit about how you want to interpret this. And then there's also this issue. Yep. No, n is the spherical harmonic index. It's the total wave number. Because if you want to look at energy and entropy, because in the z is n squared times e, z of n. So if you want to use a 2D turbulence reasoning, then you have to be working in the spherical harmonic index. Yeah. And then you'll just assume that the m doesn't matter if it's isotropic. Like from here, you might argue, well, I can just assume that everything's independent of m anyway, that it only depends on n. Sorry, m is increasing. Maybe this is a funny. M is increasing this way. Maybe that's the source of the confusion. This is actually an axis, but you only fill in this piece of it. M is increasing horizontally. Yep. This. Oh, sorry. Why is it different at different scales? We'll come to that on Friday. I'm going to try to keep it simple for today. Oh, vorticity, does that help you? It's a square of the... It's a square of the... Yeah, it's the L2 norm. Yeah. Oh, yeah, sorry, I don't have a picture. Yeah. So it's filamentary. I don't think I have a figure here, but I'm sorry, I'm having trouble with this today for some reason. Yeah, filamentary. So basically, if you have a large-scale flow, because the vorticity right at omega is just advected. If you have a large-scale flow field, some kind of large-scale shear flow, and you put a vorticity patch in there, it'll get stretched out. And then, of course, if this is unstable, you're going to get stretching and folding. Actually, it's very analogous to this, to the chaotic kind of case where you get stretching and folding of PV. So you see it in filaments. So it's kind of, the PV is stirred by the stream function. Now, of course, the PV is related, or the vorticity, I should say, is related to the stream function, so it's not a passive tracer. But if you have turbulence, you could, to first approximation, you can think of the large scales as providing the stirring and the small scales as being passive. So then you can just think of it as being filamentary. And so if you look at a map, you'll see a lot of filamentary structure. So that's the physical. Yeah, I don't know what I've done wrong here. If it's too wide, or maybe I was trying to make it too wide. That feels good. I'll just try not to move too much. Yeah, okay. Oh, no, that's not right. It's not over my ear. Okay. Actually, I went up. I don't want to spend too much time on this. I'll come back to this on Friday, but because of Brad's lectures, I thought it would be good to plant this in now because you can see a connection. So if there's an interaction between a zonal flow and eddies, there will be some nonlinear transfer. This is the quasi-linear part of the dynamics, and it occurs at a fixed zonal wave number m. So that's something that Brad mentioned too. So if you have a triad, let's say, and you have, let's just do it in planar geometry, it's easier, but the same thing applies on the sphere. If you have a zonal flow, it'll have something like this. It'll be kx equals 0 and some ky. And then if I form a triad, let's say I've got something out here at a given kx, then if I take this triad and add it to that one, I'm going to get something there or there. So I wind up generating triads that look like that. So the triad interactions with the mean flow are very special because they couple two different eddies at the same zonal wave number. And then you can imagine that in the quasi-linear dynamics, the eddies just slide up and down this scale. Now, if there's a separation in scale, as there tends to be, to a reasonable approximation, these triads have to conserve energy and entropy, but the entropy of the zonal flow is negligible. So it winds up that they essentially are conserving entropy of the eddies. So you can think of it as the entropy is moving up and down scale. But then, of course, if you move energy downscale, that implies that there must be some energy back up here. And if you move energy upscale, just from conservation of energy and energy, it means that the energy must move out. So this would be energy going out if the eddies are coming up this way, and its energy is coming back this way. Is that making some sense? Yeah. Okay, so I've got two triads here. So I'm assuming I have a zonal flow, and I'm assuming I have some sort of non-zonal wave. And then I ask, what are the interactions that are possible? So I find that there's two just in the triad, because triads have to add. So it's either plus or minus. So these are the candidates. So I have two possible triads. If I just focus on this triad, in other words, if I assume that the energy is here and this is 0, then I'm filling it up there. So I'm transferring entropy out here. then if I transfer entropy to high wave number, that means that the energy of the eddies must go down. So by conservation of energy, it must be coming back up here. So if you transfer the entropy to high wave numbers, then that implies an upscale cascade of energy. And if you transfer entropy to lower meridional wave numbers, that will imply that the energy must come this way. So this is just these Fjortoft kind of triad arguments. Okay, yeah.
When you make this argument, don't you imply that that entropy and energy are conserved scale by scale?
Triad by triad. They're not conserved in the whole thing. They're just, but it's true that the entropy is conserved for the eddies because of the scale separation. So that's sort of in that limit for its approximation. There was another hand. Yeah. The spectrum is isotropic, but not the exchange, not the nonlinear terms. Oh, it's not isotropic all the way. If I look here, down to these scales, I got in this. Look at this contours here. This is 200, so there's a huge, and actually all this stationary stuff is very anisotropic. So the large scales are very anisotropic. So what this is implying actually is that the non-local triads are quite important. Yeah. This is integrated over the troposphere. Yeah, but it's actually mainly coming. If you look at these fluxes, there we have a vertical. In the Bourne Shepherd, there's a vertical. It's coming from the upper troposphere mainly. So most of the flux is coming in the jet stream levels. Yeah. Yes. Yeah. That's just these triad interactions. If you go through the exercise, if you imagine that because if I have z is equal to k squared e, and then so there's a thought experiments. You say if I'm transferring. If I have a wave number, let's say a wave number 1 here, wave number 2, wave number 3, then if I transfer, so I can't just do this because that would violate, because I can't conserve energy and entropy if I just do that transfer. So I always have to do either that or I have to do that, right? Or, so it's got to be some triad. But if you're thinking of initially pumping energy in here and then it's got to spread out, it can either do, it's got to do both at the same time. Yeah, sorry, I guess it could be I had it the other way around as well. So depending on which way you go. So then if you just solve these, it turns out that, so energy and entropy conservation constrains what you do. Now actually it's not true that every triad, this is one of these famous things that was not quite true. It's not true that every triad gives you net upscale energy transfer and net downscale entropy transfer. It tends to be so. There's a whole stuff on that too that I won't go into. But if you just do this a thought experiment that I had here, it's the case that this means there must be energy transfer upwards, and this would mean there must be energy transfer downwards. Okay. So yes. Yes, that will come up on Friday again. Sorry, I was trying to motivate and then come back to 2D turbulence, but well, and actually this is part of maybe this is a teaser for that. So this was again in this observational data set, which I then used for my thesis, and so I say it's got this transfer. So what you can do is you can look at, this is for a given m equals 2 in this case, so these are planetary, this is zonal wave number 2, planetary scale eddies, and then I plot it as a function of n minus m. Okay, so I'm looking in the spherical case up and down here. And this is the energy exchange with the mean flow, and you see that some eddies are gaining from the mean flow and some are losing, but it's not adding up to 0, and that's because the mean flow is part of the picture too. And in fact, in this case, the eddies are gaining energy. Sorry, I should have showed this one first. So if you look here, what you see is there's transfer from wave numbers 10 to 20, more or less, both to larger scales, smaller wave numbers, and to smaller scales. So this actually is the baroclinic scales largely. So what you're seeing is that there's baroclinic instability, and the entropy is being transferred both to larger scale and small scale, and actually it's more or less equal. The first approximation, this integrates out because of the scale separation. But when you compute how much what this downscale transfer means for energy and what this transfer means for energy, we see that that the eddies are actually gaining. But if you, I'm sorry, no, sorry, forget what I said about synoptic eddies. This is planetary waves. This is m equals 7. These are the synoptic eddies. You see that they're actually their input, their energy input is coming already at very high meridional wave numbers. So there's nowhere to go. They have to go downscale, and that means there's an energy loss. So actually, what we already see is that the synoptic eddies are losing energy to the mean flow, but the planetary scale eddies are gaining energy from the mean flow. So that's interesting. That maybe tells you that there's also something that's not quite pure 2D turbulence. But that's all I want to say about mean flows today. But it ties into the quasi-linear dynamics that Brad was talking about. Okay, so Leith, Hank mentioned Leith. He was also one of the, he worked on balance, but he also worked on 2D turbulence, predictability, and so on. So he used this EDQNM, eddy damped quasi-normal Markovian closure, to estimate, because so I said one of the problems was that we don't actually, we only have data up to wave number 40. So, you know, is this the entropy flux? Is this the downscale entropy flux? You don't really know because you don't have these unresolved scales, and you're missing a whole bunch of triads. So Leith assumed, used this closure model, assuming a -3 spectrum, and then computed what that meant for the interactions. And it turns out it's like an effective diffusion, but with a negative spectral range. So this is like the effective diffusion coefficient that you derive from the closure. It may look a little weird at first, but what this will do, although this is small, when you apply this to the energy is much bigger at large scale. So actually this negative will exactly balance this positive. And so for the energy, this is an upscale. This will conserve energy, I should say. So and then we applied this to this observed data, and then so this was the observed fluxes just from the resolved scales we had, and then this is adding in the Leith thing, and now you get something that looks like what the theory would say. You have basically a zero within uncertainties downscale energy flux and an upscale energy flux, and the entropy flux seems to be flattening out. So this would seem to imply this was maybe an underestimate, but it wasn't a huge underestimate. So if we assume this closure theory, we can extrapolate, and it looks consistent with the classic theory. So people have tried to see how well that works, and this was also George Bohr, but with someone a bit later on. So then, of course, the ECMWF resolution has been increasing over the years, and I've forgotten what it actually was here, but you only believed it maybe to T60. So we could compute this essentially Leith function. You take all the wave numbers out to T60, and then you truncate back just to wave numbers up to 32, and you then compute what the missing interactions are doing to the wave numbers up to 32, if you follow me. So this is this Leith function, although there's a big difference in contour. So I can't plot these things on the same scale, right, because this is so small. So this is, now there's a factor of 10 difference in the contour intervals between the positive and the negative. But it looks like that Leith function, and actually this is now plotted against pressure. So you can see that all the action is happening around the tropopause, upper troposphere anyway, in general. And so if you apply this to the energy spectrum, this is what you get. So what you actually get is that there's an upscale transfer. So that downscale, the parent downscale transfer that we saw in the raw data was an artifact of missing interactions. And if you compute those missing interactions, you find actually that it comes back upscale. And actually, this is what's called energy backscatter, and it's used in operational weather prediction because this is felt to be an important physical process, that you're missing scales, that you don't have enough of the variance at the small scales, and so you have to excite the larger scales. So this is what's called backscatter. But then if you look at what it does to the entropy, it just dissipates. So that looked kind of promising. I guess you could, I'm using Hank's hierarchical, you have a simple model and say, how well does it work with the observations? What are the limitations? So that seemed to be promising. Then I've already mentioned Helen Burgess. This isn't actually part of her I was telling someone else last night, a good advice with a new student, I think, is just to give them something to get a first paper out, to get their teeth into something. Now, she got very interested in much more abstract things, but this was we said, okay, let's just go back and do these things now. Eastern WF is up to T799. That's pretty high resolution, and redo all this. And so if you do it, actually, this is now zonal mean and eddy rather than stationary transient, but it's about the same. Actually, this picture looks very similar, but now we see that the energy flux really does go to zero. And now so you could argue that because this is resolved now, that we have the baroclinic excitation is the range from here up to here. So where this is a flux to the left, and there's nothing happening about here. So this is implying that the baroclinic excitation is over scales 10 to 30 total wave numbers, which is smaller than the deformation radius. Well, it's deformation radius and smaller. But then if you look at the downscale cascade, actually this mixed term is relatively small now. So this, you could now say this is more like a classic 2D turbulence downscale cascade. But the upscale cascade, we still have this funny aspect that actually what looks like an upscale cascade is a mixture of very short. I mean, it's not even a cascade; it's one step. So the eddy, which would be the classic 2D turbulence, is just this very, very narrow range here. So you're never going to see a minus 5/3 there, and then actually a lot of it's carried by these mean flows. And if you look at the power law, look at that. This is -3. This is minus 5/3. Now, okay, it's not observations; it's what's called analyses. But actually, this is a forecast. So this is the analysis that. This is in the upper troposphere now. You don't get a clean -3 if you integrate in the vertical because of the boundary layers and things. But in the upper troposphere, this is the analysis that, well, and that's some other grid, but it's something like the triangular truncation. So it's like wave number 700. Do you know what that corresponds to? That's about 20 kilometers, I guess, something like that, I think, horizontal. And this is a forecast model at T1279. So, you say what do people say in New England, if you don't like the weather, just wait another day. With Eastern WF, if you don't like the resolution, if it's not high enough, just wait another year. But this is kind of a mystery. How can such a complex system as the atmosphere have such, unless you argue that the model is doing something very funny, but there is aircraft data, which I'll show you in a second. It's amazing. I mean, because you've got so much else going on. How can such a simple theory? Okay, now the other place Charney comes in here. There's this very famous spectrum by Nystrom and Gage from aircraft, and it was Charney who realized that. I mean, he wasn't. It's funny because Charney and Lorenz are just the opposites. Lorenz almost always published by himself. He was, a mathematician really in his office, and Charney was going around the world raising money, organizing aircraft campaigns, and all sorts of. He was really out. So he realized that all these commercial aircraft are actually measuring winds and temperatures as they fly, and that could be used as a data set. So that was called GASP, the Global Atmospheric Sampling Program. And Gage and Nystrom analyzed this data. So this is all from commercial airliners. And you see that there's a -3 at the largest scales, but then you get this other, which is very interesting. And so, of course, like with any spectral analysis, as Hank said, you've got to be very careful. So there were lots and lots of arguments about if this is real and to do with their how they take the measurement and everything. But I think it's really held up. Yeah. Oh no, it is. Yeah, because it's because you're inputting both. So the entropy, so this is a flux. So the flux is going from 0 up to its value. I have to well, it's the same range more or less. It's maybe a bit from an entropy point of view. You would say it's going from about wave number 10, 15 up to about wave number 50. So those are the scales that are they're forcing entropy and they're forcing energy, of course, at the same time because energy and entropy are linked. The energy input is mainly coming from the smaller wave number side of that range. Let's say from the 10 to 50 wave number range. Most of the energy is coming from 10 to 30, and most of the entropy is coming from 20 to 50. But this is, it's not as flat as you might like, but it's. Ah, clever. Um, yeah. Okay. Well, so it's an important point that the ECMWF model has all sorts of filters. It's not going to capture gravity waves because they're not in the observations, or they won't be able to pick them up. They actually want to get rid of them anyway. They do get gravity waves, but higher up. So this is probably more balanced than the reality. So I think the way I think that's an interesting point, and I think that probably means that actually I will come to that in a second. Sorry, that's the because this is going out. Mind you, this is spherical harmonic index, so we got to be a bit careful because this is a wavelength. So I think this is a wavelength. So, but you see, and these are all offset now. But it is true. This is probably coming up a bit. This is not as extensive as we see here. That's probably right. Yeah. This is global because this is spherical harmonic. So there is an issue there, and that was a possible follow-on, but Helen decided she wanted to do other things. So you have two choices, neither of which are good. So one, as in life. So either you use the spherical harmonic index, which is the natural index for the sphere, but then you have to mix together the tropics and the exotropics, which are very different behaviors, really. You could use something localized in the exotropics, but then you can't use spherical harmonics. You could take a zonal wave number, but then you don't know what to do about the meridional. You could use wavelets or something like that. Probably that's what you'd have to do, is use some sort of a wavelet transform. Yeah, so that's, of course, an issue with this, too. But it's interesting. So then I say, okay, well, actually, we have to understand k to the minus 5/3, and it's certainly not a Kolmogorov, because this is a much, much larger scale, obviously. We're not isotropic, even. I mean, the atmosphere is not 500 kilometers deep. So this has been interesting, and actually, you'll hear about this next week, because two of your speakers are in one camp, let's say. There's quite a lot of controversy. It was originally, one of the arguments is, well, maybe it could be an upscale cascade. Because I talked yesterday, there's actually two kinds of balance. There's the low Rossby number balance and the low Fruit number balance. And on the mesoscale, you don't have small Rossby numbers, but you do have small Fruit numbers. Or you can argue that. So you could argue that there's sort of thunderstorms and so on, which are generating, which are exciting the atmosphere at very small scales, 10 kilometers or so. But actually, it's exciting low Fruit number balance structures, and that could be an inverse cascade. So Doug Lilly pushed that for a while, but I think it's pretty much everyone agrees that that's not what's going on. Although it could have. So the simple, and I won't go into this, but is that if you have, so I've talked about, this is why I talked about balance and unbalance. So I won't write the equations, but if you write the energy, at least in a linear, quasi-linear decomposition, you can write the energy as a sum of the balanced energy and the unbalanced energy. I mean, to first approximation, you would take the divergent wind and the rotational wind. So if you look at the energy, if you look at the unbalanced flow, it conserves energy, of course. Everything conserves energy, but it doesn't have to conserve entropy because the PV is 0 for unbalanced flow to first approximation. So there's no entropy constraint that operates on the unbalanced flow, and therefore you argue, using the same arguments, you get a downscale cascade. And so you can argue that you'll just get if you excite in general a mixture of balanced and unbalanced motion, because we have jets and flow over mountains and all kinds of things that will excite a mixture. Some of it goes into the balanced flow, which will obey 2D turbulence, the classic 2D turbulence, and some of it will go in unbalanced flow, and that will be a downscale energy cascade. And so that's point of view has been argued by Bartello and most prominently, I guess, recently Eric Lindborg. Now, so as I say, you'll probably hear next week that there's some controversy about if it's really waves or not. Certainly, I don't really, to me, it doesn't really matter if it's waves or not. It's unbalanced, and balance is the important thing. And certainly as you go up in the atmosphere, because the stratosphere is stratified, so it doesn't have internal instability mechanisms, you could have turbulence, unbalanced turbulence in the troposphere, but that will radiate gravity waves, and those will propagate in the vertical. And the other cautionary tale, I guess, is also, Hank was saying, it's hard to falsify theories. If you go through scaling symmetry, and if you can get a -5/3 from a scaling symmetry, there's many ways to derive a -5/3. Many. I mean, you can have all sorts of assumptions that will give you, so, because actually, even if it, because the gravity waves seem to keep this, and you wonder how does that happen? Is it saturation mechanisms or? So I will say the gauge-Nystrom spectrum. And don't ask me what the difference between the blue and the red. I was looking at this last night, and I've forgotten, and I couldn't find the paper. But these guys had run a model at the day. This was 10 years ago, at pretty high resolution for a GCM, and they found that actually you do get this break between a -3 and a -5/3 in the upper troposphere. And also, Helen again in this paper had looked at Eastern Balbeuf forecast. So this is the plot I showed earlier at 250 hectopascal, and what you see is a -3. But if you go to 100 hectopascal, which is higher, what would that be? Sort of 15 kilometers maybe or something. You see there's a break here. That's kind of interesting. And if you split it into rotational and divergent flow, then what you see is that the divergent energy actually has that shallower slope all the way through at all scales, and the rotational flow, which is green, down here, seems to bend over. Actually, this is the source of the controversy, I think, between Lindbergh and so on. But anyway, you could argue that. Because there's one way to talk about if you talk about waves, of course you would look for peaks in a power spectrum or something. I mean, are these waves, or do they have the right polarization relationships or phase lags or something? But more generally, for balanced flow, we have the divergent energy is much smaller than the rotational energy, right? Because the divergence is much smaller. Then I'm using different symbols, but much smaller than the vorticity. But for unbalanced flow, for gravity waves, it depends on the aspect ratio and so on. But basically, this is going to be of the same order. So you would argue that what we're seeing here then is a hint of a balanced dynamics which is emerging at the large scales. But once you get into the small scales, it's more of an unbalanced dynamics. And the gravity waves, they get forced and they propagate up in the atmosphere. The atmosphere gets less dense, so if you conserve energy, the variance of the winds is going to increase exponentially. And there's various ways that the waves are going to break, but a lot of the breaking occurs much higher up. So basically, the gravity wave part is growing with altitude, but the rotational part is being damped. So this is what's called Charney-Drazen filtering, classic thing, that only the planetary waves get through. So what's shown here is to plot the combination of divergent and rotational energy at 100 let's start here, 250, and then you move up, lower pressure, higher altitude. And what's happening is that the rotational part is starting here, is just coming down. And so the break point between the where you go from the steep spectrum to the shallow spectrum moves up in altitude because of that. And actually, when I was in Canada, I used to be involved with a middle atmosphere model, and this was much more modest resolution, T32, you can see here. So these are going to be numbers you don't quite relate to. These are plotting on isentropic surfaces, constant entropy in terms of potential temperature. So 320 Kelvin, potential temperature is about 10 kilometers. 1000 Kelvin is about 35 kilometers. You can impress your friends with these numbers, big numbers. 4000 Kelvin is about 70 kilometers. So you see that actually if you look at the total kinetic energy, even in a T32 model, you get this sort of a -3 in the troposphere and the stratosphere, but then up in the mesosphere you get something actually very shallow. But you can see that it's just the divergent part which is growing with altitude. Did I have a hand? Yeah. Yep. Yes, that's right. Yep. No, less balanced. Less balanced. Because the balanced flow gets damped by this, first of all, by the Charney-Drazin filtering, and then the planetary waves actually break in the stratosphere, but you get gradual waves going all the way up to the mesosphere. Okay, so we just have 15 minutes. So I want to say something about predictability. This goes back to Lorenz, and Hank talked about the butterfly effect, and he talked about the butterfly effect in the classic Lorenz 63 model. But in a way, again, if you want to impress friends at parties, the real butterfly effect is in Lorenz's 69 paper. And it's a bit more subtle. So nowhere, of course, it doesn't have the chaos. That was the important part of 63. So Lorenz had this paradigm, and it's sort of the classic paradigm of predictability. Let's imagine that we observe the atmosphere perfectly with our instruments. But of course, we only have a limited spatial resolution. So we can imagine that the atmosphere is perfectly resolved down to a certain spatial resolution. Let's assume that we have a perfect forecast model. But we will have errors, and those errors will be at the small scales. And then we expect through turbulence there'll be an inverse cascade of error. And the question is, how long does it take before these errors actually reach the large scale? So it's a butterfly effect, but with a multi-scale aspect. So there's a heuristic argument, and it's in Vallis's paper. I'm going to actually, I should, I think, do I? Oh, I have to go back to this. Yeah, okay, let me just use half the board. So turns out that whether it's -5/3 or -3 matters. That's where this comes in. So in this paradigm, let's say that we have wave numbers and we have k going this way. So these are the small scales. So let's imagine that it's perfect down to some scale here, but then we have some error here. So we have some error. And then we imagine that this is going to work its way upscale. So again, we're going to use this a Kolmogorov kind of local argument. That's why it's heuristic. And actually, I have a new student at Reading, really bright guy, and he thinks that Lorenz is wrong. So we'll see. But I wouldn't put my money on that. But no, well, this is a heuristic, but it's a way to explain Lorenz's model. But Lorenz has a simplified model of how this works, so I think it's consistent. Maybe Hank knows better, but I think this is sort of a simple version of what. But Lorenz does make a lot of assumptions in his model, and the localness, I think, is a key part of that. So let's assume that we have error and it will contaminate. So let's say that we have an error at 10 kilometers, and then after some time that will contaminate scales at 20 kilometers, and then after some time that'll contaminate scales. Of course, it should go geometrically. You could pick any factor you like, but let's pick 2. I mean, it doesn't really matter. So you have, yeah. The error goes backwards. The error isn't conserved, obviously. Yeah, it grows, and it will cascade up. I mean, if it starts at small scales, then it has to go. I mean, it depends where you put the error. If you put the error at large scales, it'll go downscale. But if you put it at small scales, it's like an initial. It's like a Lagrangian. No, it's a small scale. So the error is only at, if you do a spectral, it would be homogeneous. Oh yeah, it'll be homogeneously spread, but at very small scales. Yeah, that's the sort of classic paradigm. So you say that's how long will it take? So we have a time scale. Let's call it 10 kilometers is the error time, is the time it takes for the error to contaminate. So you'd have to time, let's say it's order 1 or something. 50% is error. And then there's going to be another time scale here, 20 meters, and so on. So if you want to get up to, let's say, 4,000 kilometers or something, you're going to have to go through many of these scales. So you say that the time it takes, so let's assume that the error, let's see if I got this right. So let's say that the, if the initial error, so we worry about scale L. And let's say that the initial error is at scale L times a half to the capital N. So of course, if I make n, so n is the number of steps I have to get from my initial error. Obviously, if I take n large, this becomes a very small scale. So you have this steps, and if you just then the time it takes to lose a predictability at scale at the large scale will be, let's call it Tn, which is tau of L over 2, because it's got to come from half the scale, and it's got to come from a quarter of the scale, and so on, and you go to L over 2 to the n. So that's just a sum here of, because you probably can't read that anyway, n equals 1 to n of tau to the half. Oh, that's a typo, isn't it? It's good to use a blackboard sometimes. Little n. So you have a sum of these terms. Now, what is this? What is this time scale? So yeah, there's a couple of assumptions. One is the localness of the spreading, and then you have to decide what the time scale is. So dimensional analysis, the only time scale that you would get, if you assume it depends only on the energy and the wave number, is k cubed e to the k. So this is a spectral density, so you have to multiply by k to get energy, and then you multiply by k squared to get entropy, which has units of inverse time squared, and then you take the minus a half of that. So that's the heuristic argument for the, it's sometimes called the eddy turnaround time scale in turbulence. Okay, well, I'll go back up here actually. So it's pretty obvious if you got this. Yeah. This. Well, I want something that's got units of time, and I'm going to assume it's like a Kolmogorov argument. The only you're in the inertial range somewhere, and the only information you have is the energy at that scale and the wavelength of that, the wave number of that scale. So I have to construct the time scale out of the energy and the wave number, and the only way to get a time scale is this combination. That's the argument. So that's a local argument. You're assuming that the time scale is set by the local eddy. So I guess there are issues, and that's what my new student Adrian is looking into a bit. Okay, but you can see that if you put k to the minus 3 in here, this is a constant. So that's actually a classic property of two-dimensional turbulence, is that the eddy turnaround time scale is independent of scale, which is also argued as an argument that 2D turbulence doesn't predict its own breakdown. You don't, for example, the Rossby number doesn't grow. The Rossby number stays constant, because you can link this to a Rossby number, right? This thing compared with f is a Rossby number. But that means that if I take this limit, each thing here is a constant, and if I take the limit of n going to infinity, in other words, the limit of really of the butterfly, it's infinite. So actually, 2D turbulence is infinitely predictable, but of course, you got to worry about the order of the limits. It's still chaotic. So what you mean by this is if you set a certain threshold of error, you can keep the error bounded below that threshold for as long as I want, as long as I can control the initial error. So you can make time as long as you want, and you can always, for all epsilon, there's a delta, so you can always find an initial error that will keep the error bounded. I mean, chaotic systems are still predictable. We can send spacecraft to outer planets, and actually even weather forecasting. I should have got maps. So we were talking to someone over dinner. I mean, and so you think, predicting a quarter of a period of ENSO is challenging for models, but that's a quarter of a period. If I take a 6-day weather forecast and I show you the initial state and the state at 6 days, there will be no resemblance, and yet it can be very well predicted. So you can predict in a chaotic system, just you're limited by the Lyapunov exponent. But this thing is like a Lyapunov exponent, or the inverse. So what you're saying is that there's a Lyapunov exponent, but it's independent of scale, and if I make the path long enough, I can bound it. But if you put a minus 5/3 in here, so there's no butterfly effect in 2D turbulence in this classic paradigm. But if I put a minus 5/3 in here, then I get something different. And Lorentz did put a minus 5/3 in his paper, and it's always been a bit of a mystery to me why he did that. But it's interesting. He usually had a reason for doing it then, because at the time, of course, didn't know about gauge Nystrom and so on. Because logically, he should have put a minus 3 in. But if you put a minus 5/3 in, then what you get is something that depends on k. So now the error doubling time goes like k to the minus 2/3 or L to the 2/3. So that's saying that as L gets small, the error doubling time gets small. And you can easily show that if this thing has a finite sum. So it means in the limit of infinitely small scales, actually you have finite predictability. So this is a figure from Lorentz's paper based on this closure model. And he's got different time scales here. Just to put some sort of a... so if I just try to put some numbers on these values, so if L is 3,000 kilometers, then that would give you that the time is about two days. That makes sense, right? This is a synoptic weather system. Yep. Yes, it'll go. Yes, you have finite. No matter how small the error is, you can only predict a finite amount of time. Whereas in the first case, the smaller you make the initial error, the longer you can predict. Yeah. So this really is like a catastrophic butterfly effect. And so just to put some numbers, it's consistent with this plot. So if you take a length scale of 3,000 kilometers, that gives you a time scale of, let's say, 2 days, which is a synoptic weather time scale. If you take a length of about 10 kilometers, so let's say thunderstorms, you get a time scale of about 1 hour, which feels about right. And if you take the ratio of 3,000 over 10, so I'll see if I get this right, 2/3 is going to be like is 2 days over 1 hour. So this scaling, it doesn't look impressive maybe to 2/3, but actually it can give you quite a difference. So what this is saying is that, and so he plots this, and you see that if you go down to the kilometer scale, he got 15 minutes. So that means, let's say I have this fantastic observing system that can observe down to 10 kilometers perfectly. Let's say that we spend the entire budget on observing instruments to get to 10 kilometers. If we could somehow get to 5 kilometers, which would be a huge effort, right? I mean, space goes, it's like space cubed. I would only gain about 30 minutes of lead time on my 5-day forecast, so it isn't worth it. So this is really, I think the multi-scale of butterfly effect is really interesting. So it actually, a lot of interest is in what is the role of this minus 5/3 spectrum in the real system, and is it realistically represented? I'll just, yeah.
Is there numerical evidence that this argument works for scaling?
Well, that's what my new student's looking at actually, and finding that actually there are some problems with this. But so.
The Italian school worked a lot on the
Okay. Yeah. Okay.
I think they did some works.
Okay. People have looked for.
This experiment seems to work
Okay.
well when you indeed are in the regime such a cascade.
Yeah, and people have done some diagnostics with operational systems to kind of see how the error grows and so on. It turns out that for the current work is showing that actually the main errors, if you take an error, so this is the energy. So this is the energy spectrum. The error will always wind up to be twice the climatology, right? This, if it saturates. So then you wind up with, but then you can see if you scale by the factor 2, then you can say that the energy is kind of filling it out over time. It turns out if you look at initial estimates of initial errors in weather forecast models, you tend to find that the initial error isn't, of course, just at the small scales. It tends to be pretty uniform. And you would think it doesn't matter here because it's so small, but actually the dominant contribution, there's been people doing papers on this, is from this part, not from that part. So actually the small errors at large scale seem to be more important than these. So it's a very active area. Yeah. Well, that's a period, I think. So yeah, as a wave number, it'd be 100 kilometers or something like that.
So that means that if we have perfect observation at scale down to that the limit between the case -3 and the case -5, so we could predict with that infinite predictability.
No, because you're still missing. Well,
The error at small scale will only populate the part of the spectrum that has k to the -5. So
well, but if there's coupling between, so there is coupling between the fast and the slow because it's becoming turbulence, it's breaking. So it's. I was arguing that, of course, in the classic balance theory, you assume that these things are. If it was gravity waves, that's probably true to a large extent, although gravity waves can break. But actually, it's more like just general unbalanced turbulence, you know, thunderstorms and stuff. And so I think there is a coupling between the unbalanced and the balanced flow, and there are non-local triads. So those things matter. I should say also that this transition wave number engaged in Astrom, of course, that's in the upper troposphere. And almost certainly as you go further down, it's going to move to larger scales. But we don't have aircraft flights horizontally, you know, at 3 kilometers. So there aren't really I don't think there's at least I'm not aware of data sets that would look for this transition scale in the lower troposphere. But I would expect it would be at larger scales. Yeah.
So what's the typical signal noise ratio as a predictability limit?
Signal to noise ratio. What?
Yeah, so well, you may have some patterns that you are interested in, and you also have some like errors related with the noise. I'm wondering like, I mean, sometimes even if the noise is comparable to the signal, you can still get some useful information.
Oh, right. So, for example, mesoscale forecasting, you might have a front, but it's just in the wrong place. Yeah. So there's actually all sorts of ensemble. Actually, people are. This is all a deterministic view of predictability. So you're saying what's the difference between a deterministic prediction and a forecast? But actually, it should be probabilistic. And people are moving much more to that kind of thing, and then looking at a structure. So it depends on your metric and so on. Yeah. So this is a very naive way of looking at predictability. The operational centers actually are using probabilistic methods more and more. Yeah. Okay, Freddie first.
Maybe it's worth saying, but this is valid as soon as the spectrum are valid, and then on the larger scale you have coherent structures, and then they have a more classical type of chaos arguments
Yeah.
related to the motion of
Yeah.
the coherent structure should come up at the end of the argument.
Yeah, and as I said, actually, in practice, it looks like the dominant source of error in the current systems is the error at the large scales. So it could be so then you can yeah, look very much in those kind of chaotic arguments. Yeah, at the back.
could you use the argument about how to go from the sum down there to the scaling up there?
From here to here.
Yeah.
Well, this is just well, this doesn't relate to this. I add this and this to get that. So this is just this is saying that I'll have a predictability time, so that there's an assumption that involves a number of steps because it's this cascade. And then there's a second assumption is what sets the time scales. This is assuming it's set locally in wave number. And then this plus this gives us this. Oh, just because you need something that's going to have units of time. Yeah, that's all. Yeah. So we're at 1/2 past. Let me just quickly show. In spite of the fact that the weather forecast centers are all doing probabilistic approaches, of course, the people providing the funding don't understand this. So they're always presenting results in terms of this classic picture of forecast skill. And actually, so this is from a recent Nature paper that talks about the quiet revolution in numerical weather prediction. So this is the forecast skill of the Eastern LBF system. It's based on what they pick as a classic measure, which is a mid-tropospheric geopotential height anomaly. So it's sort of the easiest thing to get. And this is a scale over 81 to almost up to present time, so 35 years or so. And the blue is the day 3 forecast. This is skill in some measure, obviously. Red is the 5-day forecast, which obviously has less skill, and then the yellow is the 7-day forecast, and gray is the 10-day forecast. And the thick line is the north. Should be the north. It's no. It's funny. It looks funny on this scale somehow, but this is the northern hemisphere, and this is the southern hemisphere down here. So in the early 80s, there was a very big difference in skill between the northern and the southern hemispheres, and that's basically to do with the observing system. So there's many observations, more observations. Of course, all the land-based observations, well, most of them are over northern hemisphere, and also aircraft flights, so they do get commercial aircraft. Most of those are in the northern hemisphere. There were satellites, but the data wasn't used very well, and in the development of sophisticated data assimilation systems is what basically led to the fact that now the satellite data has meant that there's basically no gap between the northern and the southern hemisphere. And you see that the forecast skill has improved over time, and now they would claim that they get useful skill at the 10-day scale. But you can see that there's still, if you believe in the 2 weeks, there's still a long way to go. Yeah.
How do you measure forecasts?
Oh, I don't. I have to look. It's going to be some anomaly correlation. So of course, you want to take out climatology. So you look at the some anomaly RMS. Yeah, it's going to be a L2 kind of norm. Yeah. Because they're not getting enough money. That's what they would say. I mean, this is pretty high, right? And of course, it depends on your metric. If you look at things like precipitation or whatever, except you probably should not look at that. I guess in defense, it's probably reasonable to look at this field deterministically at these time scales. But if you want to look at, a weather field, it would be much more noisy. No, I don't know. I guess what you could say is that there was a slow increase, which is mainly resolution of the model, and then there was this jump up over time. It doesn't happen. Well, it takes time to accumulate the forecast skill because you have to average over the previous year or something, so you never get a jump. So they would say this was to do with the data assimilation, but then this slope is not very different from that slope. So I think what you're mainly seeing is the impact of the data assimilation plus this long, very slow increase with resolution. But if you believe in the butterfly effect, that would be an argument. I mean, the way I've talked about it, that would be an argument for this plateauing out, because adding more scales doesn't really help you in terms of a 3 or 5 or 7-day forecast. Yeah.
Just going back to the Lawrence picture, so if you assume that your errors are going upscale, so you basically assume your errors are in a balanced condition, right?
Well, okay. In the Lorentz model, yes, because it's just 2D turbulence. Yeah.
So basically, there is no reason to assume that your errors are only in balanced and they could be in like mixture.
Yeah. So actually,
Prediction will change, right?
yeah. So it's a question about whether it's important if the errors are in the balanced part of the flow or the unbalanced part of the flow. So in the Lorentz model, of course, it's a balanced model. In the real system, it may be unbalanced, and so that would be interesting as to whether that affects the character. Yeah, I mean, that's a question. I'm not sure if people have looked at that. That would be an interesting problem to look at, I guess. Would be like in a shallow water system or something, error growth.
If you have errors, that's like name assumption would be they are in both basically, and then
Yeah.
you also have to take the interaction term, which
Yeah.
is kind of
I think the problem would be that a lot of the unbalanced errors are, if it was just gravity waves, it wouldn't really be a problem. But it's going to be in mesoscale systems that are not very balanced, and those are going to couple to the large scales pretty rapidly, or to the balanced flow, I should say, pretty rapidly.
It seems like the lines here do cross, so sometimes
Oh yeah.
better skill in the north and the south.
Okay, so there's actually there is of course noise. Because they're only doing a finite sample, but there are variations in skill. Because if you have an ENSO, for example, it can give you more skill in certain areas. So skill can go up and down for physical reasons, because it's you're in a different climate state. And actually, when the first thing, if a center sees its skill going down, the first thing they do is they look at the other centers and see if their skill has gone down as well. And if everyone's skill has gone down, or up for that matter, then it could be some real part of the system. So there's kind of an interesting thing is actually being able to know how predictable the weather is, and that could change. And there could be conditions where the southern hemisphere is more predictable for some climate reason. It's possible. I can't think of one offhand. But so some of those blips are real, and some of them are just sampling. Oh, this thing. Oh, yeah. You can really see it here, can't you?